For example, here, we know that for any explicit time integration, the stability region is going to be a bounded region in the imaginary plane. And because the lambdas increase to the square of, to the inverse of the square of delta x. So as you decrease your delta x, the largest eigenvalue goes, the largest magnitude eigenvalue goes up very, very quickly to the square, right? So a time step limitation is going to be going down very, very fast to the square of delta x. That motivates you to use an implicit scheme if you are solving a diffusion equation, especially with a large kappa, right? So if you are solving an equation, actually not just this equation, if you are solving any equation with a second order spatial derivative in it, that is diffusive, okay? And if you know your diffusivity coefficient, kappa, is large, you should seriously consider not using an explicit scheme, because that will put a very serious limitation on your time step size. Right. So your choice of delta t in solving PDEs are usually constrained by two aspects. One is by accuracy. You want to have an accurate discretization of the ddt operator of the time derivative. The second consideration is stability. You want to have a small enough delta t so that your solution is stable. And usually, ideally, we want to have a discretization for which both considerations gives you roughly the same delta t. That will be ideal. If, for example, this is a case where your constraint because of stability is going to be much, much smaller than the constraint you would have if you only consider accuracy, then it is potentially an inefficient choice of spatial discretization, a combination with time discretization. You would think about how do I change either spatial or time discretization to alleviate this stability constraint. All right. So any questions about this analysis for the heat equation? Yes? What if you don't know what the true solution is? Here, in the stability analysis, actually nowhere did I require you to know what the true solution is, right? Yeah, the derivation has a true solution inside it, but then this true solution is going to tell you how much error is going to be added each time step. It does not tell you how this error is amplified in subsequent time steps, right? The beauty of this is that the stability analysis tells you how much the error is amplified or decayed. It is completely independent of what the true solution is. The true solution, on the other hand, is going to tell you how much error is added per time step. And if you don't know the true solution, you don't know exactly how much error is added per time step. But that is okay, because from last lecture, we can see that even without knowing the true solution, we know how the error decays or increases as you change your delta x, right? The true error from the error added per time step from the Taylor series analysis is going to tell you the error is proportional, in this case, to delta x squared times the fourth order derivative of the true solution. So of course you don't know what the true solution is, you don't know what the fourth order derivative is, but you know that it is multiplied by delta x. So if you run your simulator using two delta x's, one is, let's say, twice as small as the other. The difference between these two solutions is going to give you a pretty good information on how much error is added, because you know for one solution the error is proportional to delta x squared, and the other solution it is 2 delta x squared. Right, so the difference between them is going to tell you a pretty good sense of what the error is, without having to know what the true solution is. Does that make sense? And there is also a a intelligent way to have even a better estimate of what the true solution is if you have two solutions. One is twice as fine as the other. It's called the Richardson extrapolation. So basically you have one solution and have another solution. You can extrapolate to see what the solution might be if you have a delta x that is infinitely fine, that is equal to 0. So the resulting error is going to be only even a high order function of delta x. Yes?
Do you know how to actually derive the stability formula? How do you actually get the circle?
You want me to derive why the fourth order has a stability region of a unit circle? How do we get the circle? I think you took 1690, right? Okay. Anyway, so that's for fourth order. It's very easy to do. For other schemes, especially Runge-Kutta, it'll take more than this entire lecture for me to derive it. But for fourth order, it's pretty easy to do because, for example, if you have fourth order, you have a u of n plus 1 minus u of n divided by delta t is equal to lambda times u of n, right? So basically what you have is u of n plus 1 would be equal to 1 plus lambda delta t times u of n. So the question is, does this factor gives you an amplification or decay? Right? So this factor is a complex number in general because lambda cannot be assumed to be real. And this complex number, if it has a magnitude of more than 1, it'll give you an increase. If it has a magnitude of less than 1, it'll give you a decay. So basically, if you look at the complex plane, for any number, you shift it by positive 1. You add a real number 1 to it, and look at if it has a magnitude of greater than 1. The criterion can be pretty easy to be seen. It's going to be a circle centered at minus 1, right? So if you have everything here, this factor is going to be having a magnitude less than 1. If you are outside this region, this factor is going to give you a magnitude greater than 1. So you have instability. For any other scheme, you can derive using this principle, but the derivation, the math is going to be a lot more complicated, especially if you have a Runge-Kutta scheme. Yeah.